Hi, I'm Naomi, and I'm presenting the concept of robustness of energy harvesting systems. But what does this mean, and why is it important? Let's look at a small example. We consider an energy harvesting system with a harvester, energy storage, and application. It further has a predictor and scheduler to manage the flow of energy. We place this system in an outdoor environment for 2 years. The energy predictions in this example generated by the exponentially weighted moving average predictor, EWMA predictor, are actually quite accurate. In fact, their mean relative prediction error is only 6%. Next, we look at the scheduler. We consider a scheduler that maximizes the minimal energy the application uses. And this particular scheduler is even provably optimal when the predictions are perfect. However, perfect predictions are generally not available to the scheduler. Instead, it uses the predictions generated by the EWMA algorithm. With these predictions, the minimal used energy collapses to 66 and 73% of the previous case. This example highlights that even small prediction errors can have a drastic effect on the scheduler and therefore system behavior. We see that even though the scheduler is provably optimal, this is not the full story because it is very sensitive to prediction errors. Overall, this shows the importance of analyzing the interplay between predictor and scheduler. For the example, we assumed the harvest, store, use system model, and this is also what we use throughout this work. To summarize, energy is harvested with a harvester from the environment. It is subsequently stored and then used by the application. A scheduler determines how the application should behave in the future and how much energy the application should use. The scheduler does so by considering the current state of charge of the energy storage, as well as predictions of the future harvested energy. I will address the scale block later on. For these systems, the concept of robustness captures the effect prediction errors have on the scheduler and system performance. Related work typically evaluates the predictor and scheduler individually, but this is only the first step. The concept of robustness enables the analysis of the system as a whole. In addition, predictors and schedulers are usually evaluated for a specific set of environments, and it is not known how they will perform in other environments. Robustness also provides knowledge of the system behavior in a wider range of environments by systematically describing the effect prediction errors have on the system performance. And finally, where previously system design was performance-driven, robustness extends this to a bi-objective optimization. To describe the effect prediction errors have on the performance, we define a robustness metric R, which compares the error and performance distribution. For the analysis, we assume the prediction errors follow a normal distribution with a systematic error and randomly fluctuating errors. Other error distributions can also be considered, but in the paper we show that this does not have a great influence on the findings. From random samples from the distribution, we construct predictions and determine the system performance for these predictions. With system performance, we mean a performance metric that summarizes the important system behavior. In the previous example, this was the minimal used energy, which relates to the minimal service the system provides. But other performance metrics can also be analyzed, such as the mean duty cycle, the system's energy efficiency, or the number of deadline misses. Because the error is a random variable, the performance is also a random variable, but with an unknown distribution. We can determine the distribution analytically if this is possible, or numerically generate a large number of samples from the unknown distribution. The robustness R is then a comparison of these two distributions, which is based on percentiles. We look at how big the difference in performance percentile is between the case where there is no systematic error and when we have the error distribution that we're analyzing. This is then compared to how large the error is that we're analyzing. If the change in performance percentile is large compared to the error, then the error had a large effect. The robustness metric R is small, and the system is not very robust. Conversely, if the performance percentile does not change a lot compared to the error, then the error did not have a large effect. The robustness metric R is large, and the system is considered to be robust. We can extend this idea of robustness to analyze not just one single error distribution, but a set of error distributions. We'll look at the set of error distributions and go through the same procedure as before. For each distribution, we determine the performance metric distribution and make this same comparison based on percentiles. From all these, we take the smallest value to give a lower bound on how robust the system is against errors from this set of error distributions. As before, the larger the metric R is, the more robust the system is against errors from this set of error distributions. We now apply the robustness definition and analysis to a case study where we investigate 3 schedulers. These schedulers adapt the application in comparable ways, namely by determining the energy the application uses, but they lead to significantly different system behaviors. We analyze them both with respect to robustness as well as performance. Before diving into the analysis, let's look at how the schedulers behave. For this, we'll look at the schedulers in an outdoor scenario where the energy the system harvests is shown in light green. The first scheduler maximizes the minimal used energy and does so provably optimal when predictions are accurate. Its used energy is relatively stable and high. Secondly, a long-term energy-neutral scheduler attempts to balance the predicted energy surplus and deficit. Its used energy remains almost completely stable throughout the 2 years. Finally, we also consider a duty cycle adaptation algorithm that redistributes previously observed excess energy and deficits. Its used energy curve shows a lot of short-term variations and is relatively low. If we look at the minimal energy the application uses, we have a provably optimal scheduler, the first one. And in the example harvesting trace, we show that it indeed outperforms the other 2 schedulers. But do we know how the optimal scheduler will behave in a different environment, such as, for example, in an indoor harvesting scenario? And why would we consider other schedulers if we have an optimal one? To answer these questions, we analyze the robustness and performance of these schedulers with respect to the minimal used energy. So in the previous robustness definition, the performance metric is the minimal used energy. Further, the percentile we investigate is the median. So we compare the median minimal used energy to the median prediction error. We analyze the robustness for a set of error distributions where we vary the systematic error from 0 to 0.2. For each error distribution, we perform a large number of Monte Carlo simulations and numerically determine the median minimal used energy. The graph shows the median minimal used energy for each of the schedulers and the set of error distributions. We first investigate the performance, which we consider to be the median minimal used energy when there is no systematic error. The performance for the 3 schedulers is summarized here, and indeed, the optimal scheduler has the highest performance. Continuing to the robustness analysis, the robustness is related to the slope of these curves. If the scheduler is robust, and thus the effect of prediction errors is small, then the minimal used energy will not change much with varying prediction errors. So, the flatter the curves are, the more robust the scheduler is. We evaluate the robustness metric for these 3 schedulers and find that the LTENO scheduler has the highest robustness, but at a lower performance level than the optimal scheduler. Now that we've seen that there are great schedulers, even schedulers that are provably optimal when the predictions are accurate, we also saw that they do not perform well when the predictions are not accurate. They are not robust. But what can we do about this situation? To address this situation, we propose a method to improve the robustness of non-robust schedulers, such as the optimal scheduler. This method relies on scaling the energy prediction that the scheduler uses. We therefore introduce an intermediate step between the energy predictor and scheduler, where the prediction is scaled by a constant c. Scaling the prediction effectively changes the error the scheduler perceives. This means that when a prediction error occurs, the mismatch between what the scheduler based its schedule on and the harvested energy is not the prediction error, but instead the error is shifted and scaled when c is chosen appropriately. This typically improves the degree of robustness. We continue our previous case study and apply this method to the optimal scheduler, where before we saw that although it is provably optimal when the predictions are accurate, it is not very robust. Using a scaling factor of 1 is equivalent to not applying the method. In addition, we show the effect prediction errors can have for two scaling factors, namely 0.95 and 0.9. We see that on the one hand, the performance decreases when the environment indeed closely follows the predictions. But on the other hand, prediction errors have a smaller effect, and so the robustness increases as desired. Now that we've analyzed 3 schedulers with respect to robustness and performance, as well as applied the prediction scaling method to one of them, we validate these findings in an indoor harvesting scenario where instead of synthetic prediction errors, we use prediction algorithms. For this, we look at an indoor harvesting in 2 offices with different characteristics. The first office, location 0, has little natural sunlight, and therefore the harvested energy is tied to office hours. Conversely, the second office, location 1, is exposed to significant levels of natural sunlight. For these 2 locations, we use 2 predictors. One of the predictors has a high prediction accuracy, and therefore its prediction errors are relatively small. The second predictor is less accurate, and its prediction errors are larger. We combine the 3 schedulers with each of the predictors and record the minimal used energy, which is the same performance metric as we had investigated before. Therefore, for each scheduler, we get a minimal used energy when it uses the high accuracy predictions, and a minimal used energy when the scheduler uses the low accuracy predictions. If we look closer at the optimal scheduler, we see that there is a large difference in the minimal used energy between the 2 predictors. Therefore, the more severe prediction errors from the low accuracy predictor significantly affect the minimal used energy. This is in fact non-robust behavior and validates our conclusions from the previous analysis. During the robustness analysis, we also considered the performance of a scheduler. The performance was tied to the minimal used energy when there is no systematic error. In this validation example, the high accuracy predictor is the closest we get to that setup, and so we consider the performance to be the minimal used energy when a scheduler uses the high accuracy predictor. The optimal scheduler has the highest performance and clearly outperforms the other 2 schedulers. On the other hand, the robustness analysis revealed that the LTENO algorithm is more robust, and we can see that its performance remains roughly the same for both the high and low accuracy predictors. This means that the scheduler is not greatly affected by the varying magnitude of prediction errors, and so it is robust, as we had determined in the analysis. Lastly, the DCA algorithm is dominated both with respect to performance as well as robustness by the other algorithms. We now apply the prediction scaling method to the optimal scheduler when combined with both predictors. Firstly, we observe that prediction scaling improves the minimal used energy in the low accuracy prediction case. It does, however, decrease the performance when the environment indeed closely follows the predictions. We can see this by the decrease in minimal used energy when the scheduler uses the highly accurate predictor. Overall, we see that the difference in minimal used energy between the high and low accuracy predictions gets smaller with prediction scaling. Therefore, the minimal used energy does not drop as drastically with larger prediction errors, and we see the desired increase in robustness. In fact, we were able to improve the behavior so much that with prediction scaling, the optimal scheduler now outperforms Thiele regardless of the predictor. In conclusion, I've presented an example to highlight what robustness is in the context of energy harvesting systems and why it's important. I then briefly touched upon the system model and explained how we define the robustness metric. Then you saw the analysis of 3 schedulers with respect to their robustness and performance. We further proposed a method to increase the robustness of a non-robust system and applied it to one of the schedulers that was previously analyzed and shown to be non-robust. Lastly, we validated our findings and conclusions in an indoor harvesting scenario. Thank you for your attention.